And I'll get screen share started now. We have an hour. I want to talk about some stuff related to our research. Feel free to interrupt me at any time. I'm going to be on full screen, so it might be better to say something. I can't guarantee that the chat notification is going to pop up if you have a question. So feel free to interrupt, just like unmute yourself and say something. But I'll try to catch it as best I can. For now, can you see my entire screen? Screen sharing working okay for everybody?
Yes.
Okay, thanks. Okay, so we're an experimental group in the material science department. We do a lot of different things. You should be able to see my laser pointer moving around, yes?
Yep. Yes.
Cool,
yep.
Great. Okay, so we like to look at materials that have function where the material itself acts like a device. And so in order to do that, we have to figure out where all the atoms are in materials. And so we do a lot of crystal growth and a lot of diffraction to figure out where the atoms are in new materials. We do a lot of looking at phase diagrams. Here's just a little slice of a ternary phase diagram from a copper tin sulfide solar cell, looking at the different defects that form in different samples. We do a lot of in situ scattering, looking at how different materials form from melts and with different chemistries. And we do a little bit of thin film stuff, and we do some more advanced synthesis stuff. And the group looks like this. I have a great group of graduate students and undergrads, and Austin for this summer is going to be joining our lab doing a remote REU. And the work that I'm going to be talking about today is focusing on making new superconductors and semiconductors, supported by the US Department of Energy Office of Science. So first, a little bit about me. I came from right in here, Spartanburg, South Carolina. Spartanburg, you can sit in a Waffle House and see another Waffle House from it. That's like our claim to fame, I guess. Home of Zion Williamson. That's about all you need to know. After high school, I was actually an undergraduate here at Illinois. I was working on making ceramics. So I spent my summer after my sophomore year on campus just doing a little bit of research. And then after my junior year, I did an internship at Oak Ridge National Laboratory growing CVD diamond films. And this internship is equivalent to an REU. The national labs have their own program called SULI, which is exactly the same thing as what you're doing now. It's like a 10-week program. And so when I was finished with my bachelor's, I knew I wanted to go for a PhD, so I needed letters for grad school. And when you apply for PhD programs in materials, you need 3 letters of recommendation. And so my 3 letters were my research advisor at Illinois, who I've been doing work for since my sophomore year, my research advisor at Oak Ridge, and then my academic advisor at Illinois, who was pretty familiar with my academic performance. So if you're going for a PhD, the first 2 are really important. You need someone who can talk about your research ability over the long term, and ideally there would be someone who can talk about your research when you kind of came in, did some work quickly, and then left. Summer research experiences are really great for that second letter. If it's an industrial internship, that's also great. Someone who can vouch for that. And then the third, we also often make jokes about the third letter writer. The third letter writer just needs to be somebody who's a third human being. Hopefully someone who you got an A in their class and you ask questions. The third one is not as important. You really need 2. And in your bachelor's degree, I think the way it's structured, often we judge people if they're doing what they've been asked to do, right? That's kind of what your GPA is. You're asked to do all these tests and assignments, jump through all these hoops, and if you do them exactly as prescribed, then you get a high GPA. So that's the one quantification of that. I'm not saying it's the most important thing, but at least that's how I think about what that number represents. And then the letters are really speaking to these other soft skills, right? Can you pick up topics quickly if you have an unfamiliar project? Are you able to pick it up and run with it? Are you independent? Do you think of doing things in an efficient way or your own way of doing things that ends up helping the project? And so this is the state of where I was after my bachelor's degree. And then after that, I went to Santa Barbara to do my PhD in the materials department there. I was doing a lot of X-ray and neutron scattering and some modeling there. And I didn't know what I wanted to do. I just knew that I wanted to do research at a high level. And so in material science, that means that you get a PhD. You go directly from bachelor's to PhD. Different fields will do different things. Like in mechanical engineering, it's typical to get a master's first. And you just kind of are on this track where you do bachelor's, master's, then PhD. The materials, we kind of skip the master's and just go bachelor's straight to PhD. Along those lines, like where do you end up? When you apply to graduate schools, there's this magical thing, the visit weekend, where they take the accepted students and they fly you out to the program and you get to meet the other accepted students and talk with the faculty. And you've already been accepted. So it's not an interview. You're interviewing them. And that's a very rare thing that you get to do in any sort of job search. And so you get to go and you see, where am I going to be a good fit? And the question that I asked myself was, are there multiple groups that I think would mesh with my personality? Did I think that I would be happy in multiple groups? And in Santa Barbara, I felt like there were 2 or 3 groups where I really could have fit in. And the type of advisor, I thought I wanted an advisor who was pretty hands-on, who would be really involved in my research. And that ended up being a really good decision. But people switch advisors. And so for that reason, I wanted to be sure that I had a second and third backup just in case. And so I was there for a while doing my PhD. The PhD is a little bit different. You have your own project that you're working on. And you are trying to show that you can become an expert in it, that you can learn something new, show something new, that you can write articles and that you can give talks and communicate effectively. And so that's how you're judged as a PhD student. And then when I finished that, I went to the materials division at Argonne National Lab, which is just outside Chicago. I switched the type of work that I was doing. I started doing a lot more synthesis, a lot more hands-on chemistry, which is a little bit different from what I was doing in my PhD. And as a postdoc, you have one job, which is to do the most high quality research you can. You don't have to take classes. I didn't have to mentor anybody. I just got to do research, and that was a pretty fun time. The downside is that it's a temporary position. You really only have maximum about 2 years to get stuff done. So if you're on that kind of clock and you're already trained, you have your PhD, what you're trying to show is that you can pick up more skills independently during that time. And can you come up with new ideas, new research ideas? And so when I was a postdoc then at Argonne, I was coming up with new ideas and building those into a portfolio of what I wanted to propose to do if I became a faculty member. And then I ended up submitting that a bunch of places and ended up here at Illinois in the materials department in 2013. So that's where I've been. The group has been humming along really well since then. And yeah, this is something that we always worry about, like what is it going to be like setting up the lab? And so it always takes input from a lot of different people, and a lot of people have to work together. So it's important to have those social connections that you build up at the place where you're going to start. And I'll talk about that a little bit at the end of the talk. Hopefully we'll touch on that. Research-wise, I wanted to present 2 questions to you that we are trying to answer. We like to find new materials. And so if you're trying to find new materials, this is often what a chemist will do. And the chemists, for better or for worse, have this historical reliance on intuition. Someone will be like a good chemist because you have good intuition. And what does that really mean? And so we were trying to define how this could be quantified. And we were asking, since we're material scientists, what's the best phase diagram? We like phase diagrams. To find new materials. A desert, this is a desert, something where I have 3 elements, calcium, manganese, and sulfur. and there's nothing in the middle. There's no ternary phase. Versus a forest, something that has a bunch of different known compounds in it. Here's potassium, tin, and oxygen. And you have these 6 different ternary compounds right here. And you could make a case that, oh, I should look at this one because there's nothing known there. And so I bet no one's looked at it. So there's going to be new compounds hiding in this space. Or I could look at this one and say, ah, well, there's already 6 compounds here. So maybe there's going to be number 7. And this was our question about which one of these phase spaces would be a good place to find new compounds. And so we're going to do this first with calculation. We're going to try to predict what's there, and then we're going to do it experimentally. And then the second question that we're going to address in this part of the talk is, how can you sweep across the phase space? How can we kind of move around inside these triangles? So the first thing that you want to do if you want to find a new material is you have to understand why things form. And thermodynamics defines this. This is like what thermodynamics is. It's telling you what things are stable. And to understand that graphically, we usually plot a diagram that looks like this. We would call this a minimum free energy surface. So delta G is my Gibbs free energy. Gibbs free energy is minimized if a compound is stable. So anything that's going to form is going to make a reaction that causes delta G to become lower, right? In thermo, you set the elements to be reference points at 0. So like elemental sulfur forms these S8 rings. So sulfur's over here, it has delta G as 0. BCC iron is the ground state, it's got delta G as 0. And we know that these two things make a compound. They make iron sulfide. And if iron sulfide exists in nature, then you would assume that it has some delta G that's negative, right? 0 is up here, so FeS has a delta G that's negative, is down here. And if we're asking what is the likelihood of a new compound forming in this system, then we would do something like calculate the Gibbs free energy for it and put it on the diagram. So here's FeS2, here's pyrite. My x-axis is my composition, so it's a little bit more sulfur rich, so it's over here. And I can look at the delta G of formation of FeS2, or I can look at this number delta G hull. This is called the convex hull. And delta G hull is telling me how much more stable was FeS2 than the previous system I was examining, one where FeS and sulfur are the only ones that exist. So I want to know, are there other new phases out there left to be explored? So I'm going to calculate this value, and I'm going to look at delta G hull, and if it's negative, then yeah, this thing should form. If it's positive, then I'm going to be less inclined to think this thing is actually going to form. And so the way that we calculate this is with density functional theory. It's a computational method that is very common in inorganic material science. The only problem with DFT is that it doesn't by default capture entropy. And there's an entropy and enthalpy component in delta G. But it turns out for a few reasons entropy is not so important to answer this question. So we're going to predict and use delta H, which is related to delta G. And we're calculating this delta H hull value. And our goal in this initial project was to find new superconductors. So that's what we're going to do. We're going to go to our computational collaborators. We're going to say, I want you to find me a bunch of new compounds that have delta H that's small or negative. And so this is from Audash Narayan and Lucas Wagner, who's in the physics department here, and they give us this big list of all these compounds, and they have these cool crystal structures, and we're like, all right, this is what we want as an experimental group. This is freaking awesome. We have like all these compounds. They are selenides and sulfides, and they got iron in them and magnetic stuff because this makes good superconductors, and we're like totally amped to go and make this stuff. We look at these numbers, delta H, and we said we want this to be negative, so a lot of these are negative. Some of them are positive, but the ones that are positive are still pretty small. They're like 0.0 something, which is good. We don't want this to be more than like 0.1, or we would think that this thing is going to be unstable. So here's a great list of compounds that we should now go and make. There's like 30 things here. And so the way that we make stuff experimentally is we look at the proposed compound. This is a gold manganese sulfide. We look at the unit cell that was predicted. This one had a nice negative delta H. We load the reactants. We take gold, manganese, and sulfur elements. We put them in a glass tube. We seal it under a vacuum because it's a sulfide. It can't be exposed to air or it'll oxidize. We heat it up, we cool it down, and we look at the X-ray diffraction data. So this black curve up here is my X-ray diffraction data. And our group does a lot of diffraction, so it's really easy for us to look at this data and figure out what all these peaks correspond to. And the ones that are marked in red, this is gold, this metallic gold. And the ones that are blue are manganese sulfide, the binary MnS. And so what we can see is that, and this is just the difference curve showing that these things kind of match up. There's, in this sample, gold and MnS, an element and a binary. So this is what our after reaction X-ray diffraction told us, that we made an element, a binary, and there was a little bit of sulfur left over. And so we didn't actually make the compound that we wanted to make. So this is a bit of a bummer. Our group is really good at moving through phase space quickly. So we do like a ton of reactions. We do in situ X-ray diffraction, and we do all these tricks. And what it turned out was that everything in that list, all like 30 compounds, none of it worked. Here's just a subset of the ones that we tried and failed to make. And so we had to step back, and this is something that invariably will happen to you the more you do research. If you haven't had a research project totally tank, then congratulations, but I can assure you it's coming very soon. So the question is, if this thing failed so terribly, then what is happening? What can we learn? We know, for example, that this calculation of the enthalpy, where I was saying I want this delta H hull value to be negative or no more than 0.1 eV from the hull. I know that this is true, because if you look at all compounds that exist in the world and you calculate this value for them, it's always negative or it's positive by just a little bit. It's like smaller than 0.1. So I know that this is true. Okay, what else can we learn? The first thing that you learn is that if you keep running these calculations for delta H hull, you'll find that although all materials that exist tend to have a low delta H hull, there's a lot of stuff that seems stable, but is just not as stable as the thing that's in equilibrium. So nature, in a sense, is very cruel to you. There are ways where you can arrange these elements that look like a stable compound, but they're just not the most stable. And to the limits that we can calculate things computationally, and adding like 3D electrons is actually makes it a little bit harder. What you see is that only 10 to 20% of compounds that are predicted to be stable are actually going to be stable. This is just something nature does to you that you can't deal with. By these methods, you're just kind of stuck with this 10 to 20% number. But we had like 30 compounds that we were interested in. So if 10 to 20% of them worked, I still would have expected these things to pan out. The second thing that we had to step back and understand was the constraint about how we had chosen which elements to look for, how we had chosen which hypothetical materials to calculate delta H for. And we had used this constraint that said we're going to avoid ternary spaces that have known ternary phases. So this would be the example of like my desert diagram. We were looking at ones where we assumed that there is a ternary hiding here, despite the fact that there was no ternary before. One reason we did this is because there's a lot fewer calculations to run than in this forest case, because in this forest case, you have to examine all the known compounds too. So we're examining this constraint, and we want to see how this assumption holds up. Will we get better results out of this kind of research if we examine the dense phase spaces instead? And so here's a different set of elements. We have sodium, zinc, and selenium. And so this is also a pretty empty phase diagram. But when you run all the calculations these 6 dots here are all calculated compounds. They're at this point undiscovered. And we see this one up here is the Na6ZnSe4, and you kind of increase the amount of zinc as you go across this line to get to something that's Na2ZN3Se4. Calculate the delta H for all of them, and you're happy again because these are mostly negative values or they're very small positive values. And so this is like the previous search in the sense that these are all good. They seem promising, but it's unlike the previous search because all these compounds chemically are really similar. They all lie on this one line on the phase diagram between Na2Se and ZnSe. So they're like a pseudo-binary line right here. They all have the same elements in them. And because they're so close together in phase space, if I try to make one of these and it ends up not being the ground state, if any one of them actually is the ground state, the system will like fall into that minimum instead. And so we're really stacking the odds in our favor because we found a phase space where we have many, many compounds that look favorable and not just like one that has a 10% chance of working out. And so experimentally we go and we start making these compounds, combining elements, putting them in the furnace, seeing what comes out. We're doing this about 850C. We had a talented pair of undergraduates who were working on making these 2 materials by 2 different methods. And it turns out that when we do the X-ray diffraction this time, we see all sorts of new stuff coming out. This was a tremendous amount of work for a lot of people in the group. Agatha, who is the lead PhD student who was in charge of this, she was just awesome in the lab. Zhao, who's doing all the DFT from Anders Schleif's group, Piyush and Nitin, who are our undergraduates, and Shannon, who is another PhD student helping with all the characterization in our group. It was a real effort by everybody. And what we see is each one of these X-ray diffraction patterns looks different. The red is actually a fit that's on top of a black curve, that's the data. So all the peaks are being matched. And the blue is the difference curve under it, showing that we're getting really good matches to all these different phases. And there's all these different compounds that show up. And all these different things fall into one of 4 different types of structures. There's either this alkali zinc sulfur selenium 2, this alkali 2 zinc 2 sulfur selenium 3, or this 2,3,4 structure, or this 6,1,4 structure. And none of these compounds were known before. And so it turns out that a bunch of materials started just like flying off the presses. This is UV vis spectroscopy. It helps us measure the band gap. And so these things have band gaps that are from kind of the high 2 EV up to about 3 to 3.5 EV. So these things are medium to wide band gap semiconductors. And as a chemist, they have really interesting structures. All these materials are made of the same type of structural motif. This is Na6ZnSe4, where the sodiums are these white spheres here. The zinc is gray and the sulfur is yellow. And all the zincs are connected to 4 sulfurs, so they form these tetrahedra. And in this compound, the 614 stoichiometry with Na6ZnSe4, or you could make the potassium zinc sulfur analog. Each one of these things is isolated. We call this a 0D structure because each one of these tetrahedra is disconnected from each other. They're just kind of floating and separated by the sodiums. If you increase the amount of zinc in the structure, you get a unit cell that looks like this, and it's the same zinc sulfide units, but now they're running in these one-dimensional chains. So if you're making a semiconductor, now this means that the electrons flow through the chains. So you've created something that's like a semiconductor, but it's only a semiconductor in that direction. And in the other direction, it's an insulator. Some of the compounds have this structure where it's like a buckled layer of zinc sulfide, and these things are all more tightly connected. And here's like a top-down view of one of those layers. So now this thing is a 2-dimensional semiconductor. And there's also another structure type that gives us this 2D connectivity is this K2ZN3S4 structure. And it gives us these flat layers of zinc sulfide, but the layers have little holes punched in them. And so we do things like look at the electronic properties of the system and compare it to things that we know. And what we can see is that since these things all have similar chemistry, they're all made up of the same kinds of elements. They're all zinc sulfide or zinc selenide. They all have similar band gaps. And you can see this if you compare something that's really well known, like a well-known semiconductor like zinc sulfide. You look at the gap between the valence band and the conduction band, and it's a little bit more than 3 electron volts. And for one of our new materials, potassium 2, zinc sulfur 2, if we look at the gap between the valence band and the conduction band, it's like a little bit higher, but it's not so different. It's kind of like high 3 electron volts. But the difference between zinc sulfide and the compounds we're making is that zinc sulfide is much more isotropic. Zinc sulfide in the zinc blend form is cubic, which means that its properties in the A, B, and C direction are all the same. It's a semiconductor in all those directions. But this one, K2MnS2, is a one-dimensional compound. It's the one that has these 1D chains. So it acts like zinc sulfide, but it only acts like zinc sulfide in this direction. It doesn't act like zinc sulfide in the other directions. And so if you want to make something that is birefringent, there's a lot of stuff going on this slide. I'm not going to get into it. But because our materials have this sheet structures and these one-dimensional chain structures, they have really strong responses, optical responses in specific directions. And so we're looking here at like the dielectric constant in the A crystallographic direction, the B crystallographic direction, and the C crystallographic direction. And you see these big spikes that are present in C, but they're not present in A and B. And this just means that they have like a very different index of refraction, or they'll have a very strong absorption in one particular direction at one particular energy. And so if you're making something like an optical filter, a polarizer, or something like that, then these are very important materials. And we usually compare this to things that are kind of state of the art, like the record anisotropy is this material, BATIS3, and it has these titanium sulfur chains that are just like the one-dimensional chains that we found in our system. And so we found that this was a really effective way to generate a bunch of new semiconductors. And so if we go back and look at the phase space, like our original question was to figure out where is the best place to find these compounds. We had these computed energies, and we want to see which one of these actually formed, which ones did we really make. The ones in orange are the ones that actually formed in this particular study. And I'm going to plot, just like I did with iron sulfide, I'm going to plot my free energy surface along this line from Na2Se to ZnSe. And I'm going to do this for all 4 systems we looked at, for where we use sodium and potassium, and for where we used sulfur and selenium. And so there's 4 convex hull diagrams, 4 free energy surfaces. And each one runs from a potassium or sodium salt on one side, so K2S, to the fully zinc binary on the other side, like zinc sulfide. And we're altering the amount of zinc concentration as we go across the x-axis. And what we would expect is that, maybe let's take a look at this bottom left one. Each one of these diamonds is a calculated enthalpy, and I would expect that I can make the ones that are the lowest on this diagram if my predictions are really accurate, okay? So in this one, it totally works. In this one, totally works. It's got a little discrepancy here where I'm predicting something should be stable, but in fact, I made something that was a little less stable. This point looks fine. This one I wouldn't expect to make right because it's above the dashed line. This diagram is pretty close. It had a little bit of a swap here on this one. This one looks pretty good. This little diamond here is actually just above the line. And so we want to go back and understand how these predictions jive with my original tolerance that I said I wanted to have my delta H be 0.1 eV per atom above the hull or negative. And if you look at the y-axis of these plots, this is milli-electron volts per atom, okay? So 100 milli-electron volts, that's my previous error bar that I was using, like the top of this graph. All these compounds are actually within that error bar. But for these systems, for the zinc semiconductors, it turns out that the worst disagreement that I have, something where it's calculated unstable, but it was synthesized, is Na2ZnS2, which is this point right here. It's 0.007 eV per atom above the hull. And this number, 0.007 EV per atom above the hull, this is actually really, really small. The crazy thing is that this is so precise that if I were to measure the delta H experimentally, like do calorimetry experiment, just like you would do in like intro chemistry, we actually can't measure it to that great of precision. Because this system has so many predicted compounds that should be below the hull, and I said that magnetism was kind of bad for these predictions, because they're all zinc based, because they have a full D shell, these things end up being super accurate, and we get 9 out of 12 of the ground states made. So we get like a 75% hit rate on our predictions, whereas before in the magnetic systems, we got like a 0% hit rate. And so now that we have this knowledge that we know that this is a really effective way to find compounds, we're plowing through more phase space computationally, and we also want to understand how we can look at things experimentally. And one way that we can move through phase space in a really fun way is by using this instrument that we have. It's an X-ray diffractometer, but unlike most X-ray diffraction instruments where you run X-rays that bounce off of the top of a flat sample, we have a high energy X-ray tube. It goes in through this little window on the side. This is like a burrito sized tube furnace. It runs through this window on the left. Our sample is sealed inside a glass capillary that's about 1 millimeter in diameter right here. And then it's coming out this window on the other side and going to the detector. And so we're able to heat up to 1,000 degrees C, and we can send reactive gases through. And we're able to do chemistry kind of on the fly. If you see any diffraction peaks that pop up that don't correspond to known phases, then sometimes this means that you've made a new compound. And we're also really interested in seeing transient phases that show up when you're heating it up, but not when you're cooling it down. This usually means that you have some kind of metastable phase. Those can be very valuable because there's no other way to see them. And this we use to a pretty good effect in a different project where we were trying to find a new transparent conducting oxide. And this is actually our original lab. So what it looks like when you're just starting out as a faculty member. This was kind of 2014. There's just this leftover lab while our regular space was getting renovated, and we just had a bunch of furnaces in there. So we're kind of working in this closet-like room, using a mortar and pestle, nothing fancy. And one of our undergraduates, Chris Murray, was making this reaction where we were trying to make potassium tin oxides to make a new transparent conductor. And he got this X-ray diffraction data, and he couldn't fit it. And I said, no problem, give it to the grad student, she'll fit it. And she said, I can't figure it out either. So she gave it to me, and I said, I also can't figure it out. So it turns out that Chris had made a totally new compound. We solved the structure of it, and it's this kind of wacky oxide structure over here. It's a potassium tin oxide K2SN307. It's a new structure type, which means there's no oxide that has this arrangement of shapes in it. It has a tin here surrounded by 6 oxygens in an octahedron. That octahedron is joined to another one on an edge, and then that one's joined by a corner to this one. You kind of have these pairs of SN06 octahedra, and they make this kind of meandering shape. It kind of looks a bit like a bow tie or something. And inside the bow tie are potassiums. And so we did a bunch of different diffraction experiments to prove that this is actually the structure that it forms. And it's not a transparent conducting oxide, but it turns out it has these really big ion channels. So it's actually better as like a catalytic material or a battery material than it is at conducting electricity. But this got us thinking again that our phase space was really busy if we're making new compounds. And so here's the phase space for that system, potassium tin oxide. And what we like to do is, instead of dropping a reaction at a specific point, we can start at a phase. So we'll start at this K2SNO3 phase, have this material buy it or make it, put it in the furnace, and I'm going to move like laterally across this phase space. I'm going to change the chemistry, so I change what elements are in it. And the way to do that is we'll start with something here. If you balance the charge here, you'll see this is like O3, so that's 6 minus. K2, okay, so that's 2 plus. So that means we have 4 plus left over for the tin, right? And so if I have 2 of these with tin 4 plus, and I react it with hydrogen, the hydrogen will go into this compound and pull the oxygen out. It'll make water vapor. And it'll reduce the tin to a different compound. And so now this K2SN2O3, here's 6 minuses from O, subtract 2 plus from K, and I have 2 tins now. So this tin is 2 plus. And if I keep reacting it with hydrogen, eventually I'll reduce the tin all the way to tin metal. And so I'm kind of moving in this direction toward tin, or keeping the same potassium to tin ratio, moving this way on the phase diagram. So the idea is that we can sit in this phase diagram and move around rather than having to run a bunch of different reactions in all these different spaces. And that's something that we're working on now. Here's a picture of the furnace up and running with gas flow. And when we get the data out, what we see are diffraction patterns as a function of angle and as a function of temperature. And when you see these vertical streaks on the figure, that means that these are diffraction peaks. We match these up to phases that we know exist. And then we have this thing heated up. It goes up to 400 C. We see a total change in the diffraction peaks. And we actually can look at these diffraction patterns and see this is something completely unknown. And so we're working on figuring out what this compound is. And then we see another reaction where this changes and gets reduced. And so there's a lot of space to explore chemically. This is something that not a lot of groups are capable of doing. I'm not aware of anyone in the US in an academic lab who can do this. So it really lets us explore phase space pretty efficiently. So I wanted to run over those quick examples and just get the point across that there are a lot of new phases out there, a lot of new materials. If you can work with data, and if you have good experimental techniques, then you have a big advantage. And you just have to try to understand what the data is telling you and understand your assumptions. And then we use a lot of in situ techniques to watch things that are metastable, to try to find things that are not necessarily the bottom phase on our Gibbs free energy diagram. And we're really still starting out to understand how we can best use this information, what kind of scripts and tools are out there, and how to use it really effectively experimentally, because we're always kind of in the good position where we have these predictions and then we can evaluate them critically. So that's something that we're continuing to work on. Since it's an RU talk, Pam had always encouraged us to give a few more developmental topics in addition to just the research. So I just want to talk about your progress as a researcher. Sort of disorganized topics, perhaps. But the first thing is that we often ask people what you want to do. I do this to all of my undergraduate advisees. And some people have a really good answer for what they want to do, and some people don't. And I want to tell you that in research, a lot of people don't know what they want to do. And that's especially true for me because I don't understand what conclusion I'm going to reach when I conduct an experiment. I don't know if it's going to work. I don't know if I'm going to see something new. So I don't always control what I get to do day to day because the research controls that sometimes. And so I want to say that that's okay. When I have this nice table here, it's very, very technical. when I started grad school, I wanted to work on multiferroics. I like applied to all the best multiferroics groups across the country because I thought it was really cool area of research. I joined a group that like did a little bit of that stuff. And then when I got there, they were like, yeah, you know, you're not going to be working on a multiferroics project. So I didn't end up doing that. I like still haven't. And then as a postdoc, I thought I wanted to do thermoelectrics. So I went to a strong thermoelectrics group, but I ended up like not doing that research much at all. I did like one thermoelectric measurement, but this is not a problem. And then when I had my portfolio of ideas to be a faculty member, I said I want to do like permanent magnets. And then that project is just kind of like fizzled, and I didn't end up doing that one either. So my advice on this point is that working on something but surrounded by good people is a lot better than working on what you thought was your favorite topic, but in a group that's not as good. And by not as good, I mean with people who you don't get along with or with people who are not supportive. So you don't have to worry about knowing what you want to do. I think a perfectly good philosophy at this stage is just saying, you know, I like research, I like being in the lab, or I like doing these simulations. I want to keep doing stuff like that. And I don't think you have to be more specific than that. So you don't have to apologize for anyone for not knowing exactly what you want to do, because even if you had this grand plan for yourself, things change. You'll find new opportunities, and you'd be amazed at how like little things that pop up can change your research directions in really good ways. And also how if you find a group of supportive people, then they'll get you involved in research that maybe you didn't think was very cool in the beginning, and then you get really interested in it. So that's one big thing is as you think about how you're going to move on to grad school or an industry, you want to find things that you're interested in, because you do have to work on them, right? Like the research topic has to keep your attention. But if the people around you are supportive, then you're going to want to go into work, and you're going to want to spend time on it, and you're going to want to interact with them. And that'll be a very good thing. Okay. And then you're also in between high school graduation and bachelor's graduation. And the thing that changes once you've graduated college is that everyone is smart. Like within those of you who are on this Zoom call right now, I would make the statement that probably none of us on this call, myself included, is actually really that much smarter than anyone else. Okay, we're all smart. That's good. A lot of what you do when you're like in high school or sometimes like bachelor's, you're thinking like, yeah, I'm really proving that I'm really smart. Okay, everyone's smart. So congratulations, you've proven it already. Hopefully that's a relief and it's not an insult to you that you're not actually like smarter than everyone else on the Zoom call, but you've done it. Like that's good. You're judged more by what you do now, right? The assumption is that you're smart, and let's see what you're gonna do with it. Once you are in possession of a bachelor's degree, that means that you have this credential, right? It's a very strong thing. And moving from not having a bachelor's degree to having one is the biggest, statistically, it's like the biggest change in economics and social standing. And so the implication is that you are an expert in that field, okay? Or if you're not an expert yet, we expect that you're gonna become an expert as you go and start working and doing research and all that. So that's a good thing. That also means that you have strong social standing. You go from having no credentials to very strong credentials. And so you are now in a position of having this clout, right? And that's going to happen to you very soon. It also means that you're going to have subordinates, people who are working for you, people who are your interns, people who you have a very different power dynamic over than you've had before, okay? And you maybe already have this, like if you're doing like tutoring or something, you already have people who are looking up for you, okay? For a lot of people, finishing the bachelor's is the point where you move from this point of being a subordinate to having a subordinate. And so this means you have all these credentials, your opinion and your influence is really important. And so the question is what you want to do with it. This is inevitable, it's gonna happen to you. And you have to understand like, how are you gonna respond? So Pam asked me to give this talk, and I couldn't give the talk and not talk about some of the stuff that's going on in our country right now. I have these credentials, right? Which means you have to listen to me right now. And so I get judged based on how I respond to things. I do a lot of chemistry, and so I'm like a member of the ACS. So this kind of crossed my Twitter feed. And it's this statement on the death of George Floyd. You can sit here and like read it. We have a little bit of time. Okay. Tragic killing of George Floyd. I agree, first of all. Big tragedy. I think there are huge systemic racism problems in the US. Okay, but let's read what this statement said. This is from the ACS. Some of you on this call are chemists. The latest string of similar acts of violence, okay, has elicited raw emotions from sadness, extreme, okay. They go into like kind of management speak here. Diversity, inclusion, and respect is a core value of the ACS, okay. Global organization, we honor differences in talents, blah, blah, blah. Strengthen humanity's ability to advance solutions. Collaboration is essential to scientific advancement. And that they wrote this first. So it is also for human progress. I think you could probably like switch the clauses in this sentence. Injustice, discrimination, harassment are at odds with our core value. Okay, condemn these acts. While anger and outrage are understandable, peaceful protests are the most powerful tools to bring about needed change. So they're doing like a little bit of finger wagging here, which I thought was unnecessary. But I want you to remember this point. Your opinion and your influence is growing very quickly. You're becoming a leader in your institution. You have this RU on your CV now. People are going to be paying attention to how you conduct yourselves. Okay. Urge our members to take stock of this tragic incident, resolve to use their science and talents in peaceful and tolerant collaborations with others. I think this is a fine statement. It's fine. It looks like it was dreamed up in a boardroom. Like the ACS was saying, oh, you know, we really have to make some statement, but we're just not sure what to write. So we're going to write something really generic. I was disappointed by the ACS. As a member of the ACS, I was very disappointed to see this come out. Compare this to something like this tweet from the Royal Society of Chemistry. So this is the British version of the ACS. We stand with Black people everywhere. Racism exists in science and needs action to eradicate it. Black Lives Matter. We commit to doing more, okay? And then they follow up with a tweet saying, if you experience or witness racial abuse, please call our confidential line for impartial support. There's other tweets in this thread that follow it. And I just want to call your attention to the vast difference in the call to action between these two statements, okay? Something that's very specific, addresses the problem, shows that they actually support people by giving resources. Think about how you are presenting yourself, because you're very soon going to find yourself in organizations that respond this way or organizations that respond this way. My personal preference is that the second one is much better, okay? They're being very specific about the stance that they take, and they're being, I think, in my opinion, as best I can tell, very supportive to, in this case, Black chemists, which is a group of people who need support, who are deserving of it. And I think it's important to acknowledge that there are a lot of systematic properties of the way research is conducted, research companies, educational institutions that have built-in biases that tend to discriminate against, for instance, Black and Hispanic researchers. And so I don't want to have, we're running out of time. I don't have time to go through all the things that are on this chart. But this is essentially asking people who are in science, technology, engineering, and math, what do they think is a major reason why Blacks and Hispanics are underrepresented in STEM jobs in this country. And what you can see is, okay, there's something like less access to quality education, facing discrimination in recruitment, hiring, and promotions. And what is shocking to me is this like vast, okay, I'll take it back, it's not that shocking, this vast discrepancy between what the Black researchers are saying they think is a problem and what the other researchers are saying is a problem, especially in like discrimination in recruitment, hiring, and promotions. There's this vast chasm, 72 to 27%, okay? People are experiencing the same environment in very different ways. And I think we need to be cognizant of that, okay? So this is my last slide. I just want to remind you that you're on this RU program to do research, which is awesome. You made it, congratulations, you're smart. You need to remember that you should keep doing the right thing, find some passion that you have and act on it. Lately, I think a lot of us, if you are reading the news, you may be wondering what you can do. Can you do some outreach, leadership? I would say this is complementary to your development as a researcher, just like having hobbies is, right? It gives you something to do. It gives you something that you can prove that you're good at. It gives you something to take your mind off lab work when you need to. This is just one resource where if you're kind of disturbed by the latest murder of George Floyd, then you may want to check out this document that looks on like things, how you can respond to that, positive ways that you could make a difference and something like that. If this is not your kind of thing, totally fine. That's totally fine. Don't worry about it. My point is that you don't need to just do research to be a good researcher. It's okay to step back, find something that you're passionate in and dig into it, devote your time to something else. And regarding this last point about different people experiencing the same environment in different ways, I want you to remember that if your job is to find supportive people, your job is also to be one of the supportive people, okay? So as you move up in your education and in your research, think about what other people are doing around you that makes you happy. Who are the people who have been really good mentors to you? Who has made it feel like you belong? Who has done things that made you feel unwelcome or has been like a bad mentor to you, okay? What were those experiences like? Because very quickly you're gonna find yourself on the other side of the table and you need to be prepared to conduct yourself that way. A little bit of advice to help along these lines is that you don't have to feel bad about quitting something. If you're in a bad situation, whether it's work or personal or whatever, some friend, some mentor, some project you're on, just quit it and trust your creativity that you can find something else to do. If your experiment's just not freaking working out, just go to your next idea, okay? Find an environment that's supportive to you. Find your mentors, talk to them, find people who you like spending time with. And if there's something that comes up that is, makes you uncomfortable or you think someone is not representing your company or your organization in the best light, the best way to do it is sometimes to make an appeal to someone's emotions. And an example of this is that, for example, if in my department, I'm always really worried that maybe some other faculty member could do something that's insensitive or racist or something like that. And so if you observe something like that, then someone could come to me and say, you know, I know that you, Daniel, you really care about these issues. And so you may be disturbed to know that this incident happened, right? Which sometimes is better than trying to go directly at the person who you have the problem with, okay? And so that's an emotional appeal to me, right? Because you know that I'm going to have this like visceral reaction where I think, oh no, this is one of my peers and now I need to do something about it, okay? So find your mentors so that you can make appeals to them that would require them to make some action, okay? And so as you rise and as you continue to do research, just remember to give specific compliments to people when they do good work, okay? A lot of people feel, especially racial biases make people feel very unwelcome in certain situations. They make them feel like they don't belong. There's a lot of imposter syndrome out there. And so if someone has done work for you or they're working with you in a project and they're doing a good job, just remember to give them a compliment. Just say, you know, this is a really cool plot. I really like the way that you handled this data. I really enjoyed working on this project. It goes a long way to making someone feel welcome, and just it's a very good way to make sure that you're being a good neighbor and a good researcher. Okay, so this is what I wanted to share with you tonight.